here we are on our blank screen. Okay. Any questions on anything we've done up till now? Okay. We're in Chapter 3, Determinant of a Matrix, Determinants, and 3.1 is Determinant of a Matrix, and I think we got up to Theorem 3.1 at the top of page 107. Okay? No questions up to there. Okay? So this is telling how to expand by cofactors. Okay? Now, if you weren't here last time, you'll probably need to go back and review what they mean by cofactors and that type of thing. I'll give you the formal definition here, and then when we do one, I'll show you how it really works, you know, what makes it a lot easier. So here is Theorem 3.1, expansion by cofactors. First, A has to be a square matrix. Okay? If a matrix isn't square, you can't take a determinant at all. Determinants require square matrices. Same number of rows and columns. Okay? So, square matrix of order n. Okay. The determinant of A then, and here's a symbol for it, looks like absolute value bars, but it's around a matrix, not a number. So that's the determinant of A is given by this definition. As if you'll ever sit down and try to use this definition. It's the summation of J is equal to 1 to n. Remember, it's an n by n matrix. And you do the Aij entry, okay, times the Cij cofactor, okay? And what that turns out to be is a I1 Ci1 plus a I2 Ci2 plus AI3 CI3 plus dot 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 plus AIN CIN. Okay? Or the determinant of the matrix can be done picking a value, okay, and doing the rows. And if you do the rows, then it's the I going from 1 to n, and Aij, Cij, but this time the J's are fixed and you count through the I's. It would be A1J, C1J, plus A2J, C2J, if I could get it to right, there it goes, plus A3J, C3J, plus dot dot dot, plus A NJ, CNJ. Okay. Now, almost a lot of blah, 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 okay? I never sit down and think of it this way, but basically what you do, in this case, pick a row, okay? The ith row, okay? And on the ith row, you do the first entry of that by the cofactor of the remaining, plus the second entry there by the cofactor of whatever's left, okay? And you go down that way. Or pick a column, okay? The jth column, okay? And pick this one and do that times the cofactor here, plus this times the cofactor here, plus this times the cofactor there, and go on. Once you actually do it, it makes a lot more sense than all these letters and numbers and I's and J's and summations and stuff like this. It's exactly what you're doing, but it makes it a lot more sense, okay? Now, here's a key. When expanding by cofactors, you do not need to find cofactors of 0 entries because 0 times a cofactor is 0. Okay? Guess what that means? Pick the row or pick the column that has the most zeros in it. Cut out a whole bunch of work. Okay? And do your expansion that way. Because you can pick any row or any column to determine the matrix. Okay? And we'll see that. Okay? So the row or column containing the most zeros is usually the best choice for expansion by cofactors. Okay? Now, all this mess about cofactors, yeah, it's all true, but in reality, it's so much easier than thinking about a cofactor. So here's a determinant of a matrix of order 4. Find the determinant of this matrix. 1, -2, 3, 0. -1, 1, 0, 2. 0, 2, 0, 3. 3, 4, 0, -2. Okay? Now, what we want to do is the determinant of A. Now, how would you begin? Second?
Take the determinant of what the 3 by 3 is.
Okay. Okay. What you first do, pick your row or your column. Which one you want to choose? The third column. Pick a row or column. This is the one I want, okay? Because it has the most zeros in it. This one wouldn't be awful. That one wouldn't be awful. This would be better than either of those two because you have 2, and this wouldn't be awful. This would not, well, this wouldn't be awful. This would not be good, and this wouldn't be awful. This is the best one. You got the most zeros in it, okay? So pick that column, okay? Now, what you're going to do is go down that column doing your matrix, okay? I mean your determinant, okay? Now, all the stuff about cofactors really all gets down to, not all, but a big part of it is what sign that position is, okay? And remember the rule for how you do that? There is a rule and there's an easy way to do it. The easy way to do it is start in the upper left, where we usually do, and start heading that way. Plus, minus, plus. That is a plus position, and there's a 3 in that position. So the first part is going to be 3 plus 3 times, and now since we're using this position, we're going to wipe out that row and wipe out that column, right? And it would be the determinant of what's left. And what's left is -1, 1, 2. You tell me the rest. 0, 2, 3. 3, 4, -2. Okay. Now, I'm going to cheat on you. Okay? The first inclination would be to do this. Pick the row or column with the most zeros. 2 choices. What are they? Which row or column has the most zeros of that? Second row or first column, either one. But I'm going to show you something easier than that. Once you get down to a 3 by 3, and they're going to show you this on the next page, why they haven't already shown you, I'm not sure. Here's how you do a 3 by, you know how to do a 2 by 2. Done, okay? Cross, multiply, right? 3 by 3, there is a sort of easier way to do that too, and here's what it is. I'm going to wipe out this bar, okay? And what I'm going to do is sort of augment this with the first two columns again. -1, 0, 3, and 1, 2, 4. They're going to show you this on the next page. Now, I tend to put a bar there. This is not a matrix anymore. It is, but it's just showing you an easy way to do it. Okay? Now, you take the down diagonals, okay? So this is going to be that 3. Don't forget your 3 there. And multiply those 3 together. And what does that give you? First, what sign? Minus of minuses. Plus. And 2 times 2 is 4. So that would be a 3 times 4. Okay? Then do the next down diagonal. And you're adding still. What's your sign? No, plus. Right? Oh, wait. Is that a... No, that's not a minus. Okay, yeah. That's a 9, right? 3 times 3 is 9. Okay? Do the final one. Ha! I like that one. What's that going to be? 0, because you got a 0 in it. Okay? Now, I'm going to subtract the up diagonals. Okay? So that's going to be that one. And it's going to be a subtraction, and the sign is positive, so it stays subtraction. And what's that going to be? 12, right? 4 times 3 is 12, right? And then here's another up diagonal, and that's going to be a minus, except there's a minus in that, so that's going to be a plus, what? 12 again, okay? And finally, your up diagonal, I like that one. What's that? 0, okay? Now, these add to 0, right? I like that. So this is 3 times 13, which is 39. There is your determinant of that matrix, okay? Now, I probably shouldn't have shown you the easy way to do a 3 by 3 yet, but once you get down to a 3 by 3, that's how that's the easy way to go. Add your down diagonals, subtract your up diagonals, okay? But you start here, finding the one with the most zeros in it. Now, if you had started with this one, say, not a bad choice, this would have been a plus minus plus 0. 0 times that, nothing. That would then be a minus 2 times, and then you do that 3 by 3, and the 0, that wouldn't do anything, and that would have been a plus minus plus minus plus minus, another minus 3 times this, and you do that diagonal. Okay? So, however you choose to start, go for it and just make sure you get everything covered. And the more zeros you got, the better, because it makes it easy to do. Okay? And I sure hope the answer is 39, and it is. Okay. Now, they did it long way, correct way, perfectly fine, but the rather than using the -1 to the I plus j, just do plus minus plus minus plus. I mean, it works, and you don't have to worry with that. And then rather than splitting it down to 2 by 2s, which you could have done, you can just do that little trick with 3 by 3s. There aren't any tricks for 4 by 4s and higher. The 2 by 2s are easy. 3 by 3s are not bad. The rest of them you have to do this way. Eliminate down. Does that make sense? Okay. Now, and I just showed you the new way at the top of page 108. If you want to see the formal written out way of doing it, there it is. Okay? Now, ready for example 5? Okay, let's do example 5. The determinant of a matrix of order 3, find the determinant of this matrix. A is equal to 0 to 1, 3, -1, 2, and 4, -4, 1. Okay. What would be your approach?
Find the row or column with most zero.
Okay. That's certainly a good thing to do. But since this is a 3 by 3, you can use a shortcut and avoid that. Now, if one of those rows or column had 2 zeros in it, I would definitely go that route, okay? But since the most is only 1, you got 2. Either way will work. What you just said would be fine. First row, first column, either one of those would be fine. Or you could do it the shorthand, okay? Which is, you tell me. I wanted you to, I'm going to erase that, and you tell me what to write. 0. 2, yeah, 2, that's fine. 3, -1. 4, -4. Either way you want to do it, down columns or across rows, it doesn't matter. You only do the first 2 and repeat them, okay? And now, what do we do?
Draw a diagonal line.
Yeah, you're down diagonal, and what's the first one? Is what?
Oh, sorry.
0. Okay, I like that one. The next one is 16. The next one is -12. Okay, then do what? The up diagonals, and what would that be? Second? Except the up diagonals are negative, so that would then be +4, right? By that? Okay. Next? 0. Okay, I'll buy that. I don't know why my 4 didn't write. Okay, and then the final one is -6. Perfect. So let's see what we've got. Okay, let's add our positives. That's going to be 20. And subtract our negatives. That'll be 18. And that's going to be 2. Okay? Yep, that's what they got. The other way would work too. As long as you do it right, you'll get the right answer. The determinant of that one is 2. Now, a lot of time, the thing we're most interested in is whether the determinant is 0 or not 0. But there are times that we do need to know what the determinant is, and that is 2. Now, before we move on, at the very bottom of the page, page 108, there's another linear algebra applied problem, and it's talking about continuous functions, x, y, and z continuous functions, of some other variables, u, v, and w. So x, y, and z are not your independent variables, they are the dependent variables, and your u, v, and w are your independent variables. Okay? And these x, y, and z, the functions, continuous functions, have continuous first partial derivatives. Then we define what they call a Jacobian. Okay? And you can do that for a 2 by 2, a 3 by 3. I have never seen one for bigger than a 3 by 3. I imagine you can. I can't imagine who would want to, but you can do it. Okay? This gives you volumes of solid regions and other things like this are the Jacobian used for. Now, they don't mention who in the world, I'm assuming Jacob was. I don't know if that's the first name or last name. I'm guessing a last name, who came up with this Jacobian. But, just a little bit of excuse for a advertisement here. Research papers, okay? Remember, those are due before the end of the month. And of this, one of my best classes, of course, I have received one. So please, folks, don't forget about your research papers. Get those in. I was suggesting possibly who was this Jacob guy that came up with the Jacobium? How did he come up with it? What's it used for? You know, there's tons of paper topics just there. Lots of others you could choose to. In fact, in my last class, Pratisha and goodness gracious, I'm going to blank on Lauren are both in my differential equations class, and we were just doing something that's not quite a Jacobian, but fairly similar to it, the Wronskian, okay? And that was using determinants, and I was having to show them, though I didn't quite get that far to show them how to do a determinant. Y'all know, they didn't. Okay, now, let's go back to, it's almost revisiting an old topic, okay? And this old topic are your triangular matrices. Okay? Remember we had these before. Remember we called them UNL. Not University of North Alabama, but UNL. University of Nebraska-Lincoln, that was UNL that I've been to. But that was the upper triangular matrix or the lower triangular matrix. Well, just triangular matrices in general. Recall from section 2.4 that a square matrix is upper triangular when? What makes it upper triangular?
The lower left is 0.
Okay. Find your diagonal. It has to be a square matrix. Find the diagonal. Everything below that, 0. Every entry below the diagonal is a 0. So all your non-zero entries are in the diagonal or above it. And a lower triangular matrix would then be everything above the diagonal is 0, everything below it will be not necessarily non-zero, but all your non-zero entries are there. Okay, now, what do you guess you would call a matrix that is both upper and lower triangular? How would it look? How would it look?
It was upper and lower?
Yeah.
You just have the diagonal?
Yes, you'd only have non-zero entries on your main diagonal. That's absolutely right. Okay? Because everything would have to be below it, zeros for it to be an upper triangular, and everything above the diagonal would have to be 0 for it to be a lower triangular. That means the only non-zero elements you have are on the diagonal. And we call those, guess what? A diagonal matrix. Okay. Now, to find the determinant of a triangular matrix, either upper triangular or lower triangular, okay, let's see what we got. Let me write a couple of these out here. Here's an upper, okay, A11, A12, A13, dot, 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 A1N, okay. And if it's upper triangular, what's that first entry? On the second row. 0. And this would be A22, A23, dot, 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 A2N. Next entry. 0, 0, A33, dot, 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 up to A3N. And then we'll dot, dot that on down until the last row will be a 0, a 0, a 0, a dot, 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 and finally an A sub N, N, and everything else Here's a dot dot. Okay? Now, if you were going to do the determinant of that matrix, what choice would you make first? Finding the determinant, what do you look for? Yeah, the row or column with the most zeros. And you have two really good choices here. What would they be? The first column or the last row, right? Because those only have one entry each. So you would just, I'm going to use this one. That would be A11 times, okay, what's left. Okay, so that the determinant of this matrix, I'm going to call this U, matrix U, upper triangle. The determinant of that matrix is going to be A11 times the determinant of what's left. Now, to find the determinant of what's left, you see the matrix is left. What's the logical choice? First column again, because it only has one entry. It's not zero. So that would be times A22. Okay? Okay? And I'll wipe out that row and that column, and what's your next best choice? A33, because it has all zeros below it, right? So that would then be times A33. Okay, wipe out that row and that column, that row, whatever, and you keep on going, and guess what you get? You merely get the product of your diagonal, right? Because all these others down here are zeros, and you don't get anything else except those diagonals. And the same thing holds for a lower triangular too, okay? The lower triangular would look like this, A11. What would be next? Zero, zero, dot, 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 zero, okay? A21. A22, 0, dot, 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 0. A31, A32, A33, and then all zeros to that one. Okay? Dot, dot, dot to AN1, dot, dot, dot to AN2, dot, dot, dot to AN3, and a dot, 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 and a dot, 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 until finally you get to ANN. Okay? And if you're doing the determinant of this one, what would be your logical choice? Find the determinant. Either the first row or the last column, because they only have one non-zero entry in them. So that determinant of the lower triangular matrix would be A11 times, and then you wipe out that row and that column, and then you would do the next one. Well, I would go with this one, so that'd be A22, and when you wipe out that row and column, then it'll be times A33, and you keep on going down, okay, until you get to ANN, and again you have the product of all your diagonals. And that's all, folks, okay? That's it. So any triangular matrix, upper or lower, your determinant of that is just going to be the product of your diagonals. Now, something that springs to my mind then, if anything on the diagonal is a 0, the matrix has a 0 determinant, right? And then that tells you something about that matrix. So basically, for these to be your ones you really love to play with, you want all those diagonal entries to be non-zero, okay? But we're not doing that yet. So, theorem 3.2, if A is a triangular matrix of order n, has to be square, remember, then its determinant is the product of the entries on the main diagonal, always. We just sort of walked through it. So let's do example 6. Okay? Any questions before we do it? Example 6. Here's matrix A. 2, 0, 0, 0. 4, negative 2. 0, 0. Negative 5, 6, 1. 0. 1, 5, 3, 3. Find the determinant of A. What you get? Anything? Negative 12. All you do is multiply those diagonals. Is do the product of the diagonal. 2 times negative 2 is negative 4 times 3 is negative 12. Done. Because all the other products of everything else are going to involve a 0. And that's going to be 0. So that is really easy to do, the determinant of a triangular matrix, either upper or lower triangular. Just do the product of your diagonals. Okay. The proof for that theorem we just talked about uses what they call mathematical induction, which is sort of a fun little thing to play with, but it can be a little tedious. If you want to see a discussion of that, go to appendix, and you'll find a discussion on mathematical induction. Okay, that finished section 3.1. Homework exercises here. Any of the odds, 1 through 11. 11 is sort of an interesting one. Either 13 or 15. Do 17. And by the way, the reason I say odds, the answer to the odds are in the back of the book. Also, calcchat.com has worked out solutions for the odd number exercises. So if you work the things, check your answer in the book, you see it's different from the one you got, see if you can figure out why you missed it, if you missed it, and if you can't figure that out, then go to calcchat.com and hopefully that will help. If you still don't understand or how they did it or why they did something, then bring it to class and we'll work those in class. So I got up to 17, then do any of the odds 19 to 31. There's some big old hairy matrices there, but some of them are quite easy to do because even though they're big, they are, if they're not triangular, they're awfully close to it. Okay? Then do number 33. Either 35 or 37 or both. 39 or 41 or both. Do 43. Either 45 or 47 or both. And then a couple more interesting ones, 49 or 51 or both. Okay. Either any of the odds 53 to 57. I would do 59. Then try any of the odds 61 to 65. Try 67. And try 69. Okay. All right. Any questions? Now, again, we're going to backtrack just a little and combine two things. One, we just talked about determinants, and one, we talked about at the end of the last chapter, elementary operations. Elementary matrices, elementary operations. Okay? Now, these start a little tedious. Okay? So bear with us. Okay? Here is a matrix that we're looking for its determinant. 1, negative 2, 3, 1. 4, negative 6, 3, 2. Negative 2, 4, negative 9, negative 3. 3, negative 6, 9, 2. Okay. B, the determinant of B, would be the determinant of this matrix. 1, negative 2, 3, 1. 0, 2, negative 9, negative 2. 0, 0, negative 3, negative 1. And 0, 0, 0, negative 1. Okay. Now, let's do either one of them. Which one you want to do? Figure the determinant. Say again? B? Really? Has all those zeros in it, though. Is that fun? Yes, it is. Yeah, B is much easier to do. A? Not a single zero to be seen. So what I would probably do is probably pick that first row because the numbers are smaller, and we're going to have to go down that. So what we would do is 1 times, and wipe out this and this determinant, and then I have to do that 3 by 3 thing and figure its determinant. And then I'll do a minus 2 or a plus 2 times the determinant of this one, which uses that, plus a 3 times the determinant of these, which you have to use a 3 by 3, minus a 1 times the determinant of this one, which you have to do a 3 by 3. Doable, but long and tedious. Whereas, what's the determinant of B? Say again? I can't hear. Did you say 10? 6. Okay, 6. Very good. I can't hear. Yes. Minus times minus is plus. 2 times 3 is 6. 6. Now, guess what? Notice the first rows are the same. If you row reduce this one, you get that. Now, the question for that is, how does that affect the determinant? Okay? And that's what we're doing now. Because how do you row reduce this? Using your elementary row operations. Remind me what they are. Switch any 2 rows. A multiple of 1 row from another row. Exactly. Multiplying 1 row by any non-zero number. Exactly. Okay. Now, each of those will have some impact on the determinant. Usually not a huge one, but usually some. Okay? So you'd have to keep up with your impacts. But, just a little bit of a hint here, because they're not getting these to be all ones here, it looks like to me they're only using one of those elementary row operations, and that would be a multiple of one row added to another. Okay, so that may be the only one we really have to worry with. Let's see. Okay. Guess what? They're going to have us do A. We've already done B. Already said that's 6. Y'all were good. Quick. Let's do A just for the practice of doing determinants. Okay? Where will we begin? Okay, the upper left corner, and that is a positive position, and it's a 1 there, so it's going to be 1 times the determinant that's left. If I wipe out the row and column, that would be a -6, 3, 2, 4, -9, -3, -6, 9, 2. Okay? And what would you do to continue that? It's the trick. Yeah, repeat those first 2 columns. -6, 3, 4, -9, -6, 9. Is that right? Yeah, okay. Okay, then let's do it. Okay. Now I'm going to write this as if it's a matrix just because I want to cut it off there. Let's go on and do the next one. The next will be, and to keep it from being as confusing, I'm going to remove my construction lines here. The next entry down that row, I chose to use the first row, is a -2. But before I write it down, what is the sign of its position? Negative. So it's a -2, which would be a +2, right? And then I'm going to wipe out that row and that column, okay, and write down the matrix that's left. And what is it? 4, 3, 2. Go on and give me the next 2. Okay, -2, -9, -3. I'm not writing very well, Emma. 3, 9, 2, and go on and do the first 2 again. 4, 3, -2, -9, and 3, 9. Okay, yeah. That's not really a matrix, so I'm going to close it off that way. And then, and this, yuck! Okay, hit the wrong key down here. Yeah, that's the one I was going to hit. I'm just going to wipe out that one because I'm always going to do the first row. Okay. Now we go to the third position in that row. And what position is that? Plus or minus? Positive. So that's going to be a +3. And what would be the matrix that I have left over there? 4, -6, 2. I'm going to go, all right, 4, -6. Okay. Next. -2, 4, -3, -2 and 4, and 3, -6, 2, and a 3 and a -6. Okay? And then finally the last one. And what position is that? It's a negative position, and the number is 1, so that'll be a -1 times, and what's left when we wipe out that row and column? 4, -6, 3, 4, -6, okay, -2, 4, -9, -2 and 4, 3, -6, 9, 3 and -6. Okay. Yep. Okay. That's going to do it. So that's going to be 1 times. Okay. How do we do those 3 by 3s? I'm hating this. You're down diagonal. And what does that come out being? $108. Okay, it's 54 times 2. Okay, then going to be a plus because minus times minus is plus. And what? 54? Is that what you said?
Mm-hmm.
Good. Okay, next, another plus. And what's that going to be? 72. Is that what you said? Excellent. Okay. Now, do I need to erase those down diagonals, or can you read okay if I just write it up? Okay. And then what do I do here? It's going to be a minus because it's going up diagonal, and you got two minuses which make it a plus, so that keeps it minus. And what's that? Second? 108 again. Okay, I like that because that gets rid of my 108s. Those are big numbers. Okay, next. Another minus, isn't it? Because it's up diagonal minus, and two minuses make a plus, so that leaves it minus. And that will be 18 times 9, I think is 162. I'm doing it in my head, so check me.
Yes, you're correct.
Okay, and then the last one. It's also a minus. 24. Okay. We got some work to do, but let's get back to it. Plus 2 times, and now we do the same thing here. Now this one I didn't do my columns so nicely, so do this. What's that? Yeah, negative 72, isn't it?
Yes.
Okay. Okay, that's 9 times, whoa, 6 times, is that right? Yeah, that's right, okay. Next, again a minus, 27. Okay, and then this one, again a minus. I think it's 36, isn't it? 2, 2, and 9. Isn't that 36? 2 times 2 is 4. Yeah, okay. And then this one. It's a plus, isn't it? Because you have, it's up diagonal, which is minus, but one minus makes it a plus, okay? And that is 6 times 9 is... Oh, 54. Wait. Yeah, I'm lost in space here. 6 times 9 and 54. Did I make a mistake like that before? Oh, that's 8 times 9, 72. Yeah, okay, got it. Okay, and this one is going to be a plus again, because it's up diagonal with minus, but then a minus is going to be a plus, and that's going to be 12 times 9 is 108, isn't it?
Yes.
Okay, and then this up diagonal, that happens to be another plus, because it's up, it's negative, but one negative makes it a positive, and that's going to be 12, right? Okay. Okay, plus 3. Now we'll do this one. That's going to be a 32. That's going to be a 54. That's going to be a plus again, 24. Okay, your up diagonals, that's going to be a minus 24, right? I'll just wipe those out. And this will be an up diagonal, which would be a minus and a plus, so it's still a minus. And that, I think, is 72, isn't it? Okay. And then this final up diagonal on that one is going to be a minus again, because minus being up diagonal and two minuses make a plus, but then minus, okay. And that's a 24 again, isn't it? Is that right? Okay. And I got one more here. Yuck. I'm going to write it up here. Minus 1 times, okay, down diagonal here would be, yo, someone with a calculator, I'm tired of doing this in my head. 16 times 9. What you get? Or 36 times 4. What you get? Say again? 144. I should remember that. Okay, this will be a plus here because you have two minuses. Goodness, these are big numbers. That's 18 times 9, that's 182 again, I think, isn't it? No, 162. 162. Yeah, okay. And then this one is again a plus because it's two negatives, and that's going to be 36. Is that what you said? Okay. What's that? It's 3 times 2 times 6. Yeah, okay. I think that's 36, right? Okay, the up diagonal is going to be a minus. 9 times 4 is 36, so that's going to wipe that one out. And this is going to be another minus. And boy, 213? 216? Okay. And then the next up diagonal is going to be a minus also. And that's going to be 54 times 2 is 108 again, isn't it? Is that right? All right. Pull out the calculators, folks. I'm tired of doing this in my head. 54 plus 72, that's 126. Minus 162 would be a minus, well, do it on your calculator, okay? And, I mean, it's pretty easy to do, okay? So 54 plus 72 minus 162 minus 24 plus 2 times 72, negative 72 minus 27 minus 36 plus 54 plus 108 plus 112, close parentheses, plus 3 times, open parentheses, 32 plus 54 minus 72 minus 24, close parentheses, minus 1 times 144, open parentheses, 144 plus 162 plus 36, oh wait, no, plus, minus 216 minus 108. Close parentheses, equal what you get. I hope you got a 6, because that's the answer. Okay. If not, we made a dumb mistake somewhere. But man, wasn't that so much easier? Big time. Were we guaranteed they're going to be the same answers? Not necessarily, unless we get a few more things under our belts. So let's see if we can get them under our belt. Can I erase it? Are you still entering numbers? Did anyone get 6? You did. All right. That makes me feel good. Warm and fuzzy inside. Okay. Let's do example 1. Here's the determinant of matrix A, which is the determinant of 2, -3, 1, 4. 2 by 2s, I like these much better. What's that determinant? 11. Okay. Now we're going to do the determinant of B. B is going to be 1, 4, 2, -3. What's the determinant of that? -11. Okay. Now this is just one example, but if you think about it very hard, you see it's always going to be the case. For a 2 by 2 matrix, if you exchange 2 rows, you get the negative of the determinant. Okay? Exchanging 2 rows gets the negative. Now, what I have to convince you to believe, for any size matrix that's going to work. Exchange 2 rows, you negate your determinant. That's the A part. So let's go back to A again. Same, no, it isn't the same, is it? 1, -3, 2, -4. Okay? You tell me that determinant. Two. Okay? Now, here's what I'm going to do. I'm going to come up with a new matrix B, which is row equivalent to this one. I'm going to do row 2 minus 2 row 1. Right? Row 2 minus 2 row 1. What would be the... Okay, since I'm using row 1, I'm going to leave those elements alone. 1, -3. Okay? And you tell me the new 1, 2 element. Second? Second? 0? Is that what I heard?
Wait, how did you get 0?
Okay. Row 2 minus 2 row 1. I'm just doing a row reduction. I want a 0 here. How do you get it? Row 2 minus 2 row 1. Right? But now you got to do it over here too. What would that give you?
2.
What's that?
For row 2, column 2, 2.
Okay. What'd you get? 2?
Yeah.
Okay. I'll buy that. Okay. Now, you give me the determinant of that. 2. Hey, look at that. At least for this one, adding a multiple of one row to another row, you don't change your determinant at all. Okay? Now remember that first one we did? I said it looked like to me that was doing only that operation. And sure enough, that 6 stayed a 6, no matter how many steps you did. Okay? Now, what's the third thing? Start with matrix A, determinant of matrix A. That'll be 2, -8, -2, 9. 2, -8, -2, 9. Okay? And what's the determinant of that one? Second?
34.
Okay. That would be 18, right? Minus 16. Not added to 16, minus 16, right? And that is 2 again, right? Now, we're going to do something to this. That first row we're going to, what would be a logical thing to do to that first row? Huh? Divide by 2. So it would become a, no, let's divide by 2. 1, negative 4, right? And negative 2, 9. Oh, you've already done the, okay, I got it. And what is your determinant of that? 1. Okay? So if you divide a row, and later we'll even know a column by a number, you divide the determinant by that same number. Or if you multiply a row or a column by a number, you'll multiply the determinant by that number. So exchanging 2 rows changes sign. Adding a multiple of one row to another doesn't change the determinant at all. And multiplying a row or a column by a number, you do the same thing to the determinant. Multiply that row or column. Multiply the determinant by that number, same number you get. This was a 1/2. It could have been a 3. It could have been anything. Okay. Now, goodness gracious. My head just clogged up something fierce. Okay. And I did see somebody have to go out. Do you need to take a quick break? Would it be beneficial? Okay, let's do that. Okay. This leads to, the 3 examples we just did, leads to theorem 3.3. Okay? Elementary row operations and determinants. A and B have to be square matrices. Okay? And they don't say they are the same size, though. Square matrices of the same dimension. Okay, number 1. When B is obtained from A by interchanging 2 rows, okay? Now, in a short while, we will then extend this to or columns. So I don't see why not do it now. 2 rows or columns. We've not done that before, but we can do it when we're doing determinants, okay? Rows or columns of A, then the determinant of B is equal to minus the determinant of A, okay? That's what the result is. So 1 row operation, exchanging 2 rows, changes the sign of the determinant. Okay? Number 2. When B is obtained from A by adding a multiple of one row to another, or column. We haven't done this before, but we will soon learn that we can. Adding that to another, the determinant does not change at all. The determinant of B is equal to the determinant of A. And that's our favorite row operation to do, elementary row operation to do, adding the multiple of one to another. And it doesn't change the determinant at all. And then number 3, when B is obtained from A by multiplying a row of A or column, a row or column by a non-zero constant okay, C, then the determinant of, I hate writing it that way, and I did it. The determinant of B is simply C times the determinant of A. I mixed my notation there, but there's what we got. When B is obtained by multiplying a row or a column by a non-zero constant C, then the determinant of B is that constant times A. Okay. And they have a little proof there, and you're certainly welcome to go through it. They also have a little blurb here on Augustin Louis Cauchy. Okay? He is incredibly often credited with bringing rigor to modern mathematics. Okay? The first to rigorously define limits. Sure, Newton and Leibniz had to basically talk about how you get derivatives and stuff, but didn't go into it to the rigor that Cauchy did. And just looking at him, he appears to be a very young man, and looking at the dates, well, he did live to be 70, wow. So he was a fairly old man. The picture is quite young looking, though. But he did more than that, rigorously defined limits, continuity, convergence of infinite series, complex analysis, determinants, differential equations. Goodness, is there anything he didn't do? So I think we owe him some of the stuff we're doing now was the result of his development. So let's do example 2. Okay? Here's a matrix A. Two, negative 3, 10. 1, 2, negative 2. And 0, 0, negative 3. Okay. Says find its determinant. Okay? That's not a hard thing to do. How would you do it? How would you determine the determinant of that? Second? You're going to swap? I would too, okay? But actually, my first bet would say, no, let's just do the determinant, okay? There's a row with 2 zeros in it, right? So let's pick this row here, and we're going to do it. You don't have to do anything with that or that. Let's just do that. First, what is the sign of this position? Plus, okay? By the way, if you haven't noticed it already, all your main diagonals always plus, okay? Plus, minus, plus, minus, plus. Plus, minus, plus. You have no way out, plus, minus, plus, minus, plus. No matter how you get there, the diagonal is always going to be a plus, okay? So that's going to be a plus, but it's a negative 3. So that determinant is going to be negative 3, times, and then wipe out that row and that column. And what do you have here? 7. So this is going to be negative 21. Okay. Now let's do it Lauren's way. Okay. We're going to row reduce this. And she said exchange 2 rows, row 1 and row 2. Okay. So that will now be The new matrix is going to be 1, 2, negative 2, 2, negative 3, 10, 0, 0, negative 3. All right? But what did doing that do to the determinant? Exchanging two rows. What did that do to the determinant? Oh, so long ago. It negated it. So just remember, we have to negate the determinant. Okay? Now, what's the next thing you want to do? Second, get a 0 below that 1, and how do you get that to happen? Say that again. Negative 2 times row 1 plus row 2. Yeah. So I'm going to do row 2 minus 2 row 1. Okay. Same thing. All right. All right. And what's that going to do to the determinant? Nothing. Remember, that's the operation that doesn't change the determinant at all. Okay. Changing two rows negated. This doesn't do a thing. So 1, 2, negative 2. And we're going to leave 0, 0, negative 3 there. And then what's your new row 2? 0. That is a 0 there too. Okay, say that again. Okay, negative 3 minus 4, isn't it? Isn't that a minus 7? Yes, negative 7. And it's a 10 plus 4. Is that 6?
Let's just do a negative 2 times negative.
Okay, yeah, my eyes are hurting. I can't read. 2 minus 2 is 0. Negative 3 minus 4 is negative 7. And 10, plus 4 is, okay, 14. Is that what you said? Okay, I'm sorry. My eyes are just stinging like crazy. Okay. Now, I think we can just go from here, can't we? Okay. Because what kind of matrix is that? Upper triangular. And what's the determinant of an upper or lower or any triangular matrix? Product of the diagonal. What's the product of the diagonal? 21. And then because we exchanged two rows, negate it. Yep. Negate 21. Okay? That's it. Now, that was awfully easy to do that way, but it was pretty easy to do this way too. Okay? All right. Any questions on that? Okay. Now, what they did the row operations with the indeterminate form. So they went from this to minus that. Okay, just wipe out the yuck. This isn't. Okay, we won't call it that anymore. We'll do actually the determinants. Okay, so we'll do that is that, which is the minus of this because we exchanged two rows, which is the minus of that, and that indeed gave us minus 21. Yeah. Okay. That's how they wrote it, and which is fine. Okay, any questions? Now, I told you before we were going to do this, and now they're doing it. I just let the cat out of the bag a little bit early. Although Theorem 3.3 says rows, I kept saying or columns, and that's exactly what they're doing at the top of page 114. Although 3.3 stated that in terms of elementary row operations, the theorem remains valid when the word column replaces the word row. Operations performed on columns rather than rows of a matrix are called elementary column operations. And two matrices are column equivalent, not row equivalent, but column equivalent, when one can be obtained by the other elementary column operations. Now, don't go around doing this if you're trying to solve a system of equations, okay? Exchanging columns or multiplying by columns, that doesn't really make a lot of sense in that respect. But when you're doing determinants, it doesn't matter. Determinants have nothing to do, or not too much to do, with what you were doing before, okay? So, let's show a couple of examples. Well, my cursor disappeared. Here is a matrix that we were wanting to take a determinant. 2, 1, negative 3, 4, 0, 1, 0, 0, 2. Okay? Now, I see no problem taking the determinant of this as is, okay? Pick the row with the most, the row or column with the most zeros. That either the second row or the second column or the third row. I go with the second column because it's simpler, or 1 there rather than 2 here. Okay? I'll look at the placement of that. What place is that? Positive or negative? Negative. So it'd be a negative 1 times 8 minus 0, that'd be negative 8. I mean, you can't get a lot easier than that, can you? So the determinant of that is negative 8, okay? But for those purists among you who are so lazy you don't even want to think that much, notice that you can exchange these two columns, and that gets it in upper triangular form. So what we're going to do is exchange those two columns. So this will be the minus, because exchanging two columns changes the sign, okay? And that will be a 1, 0, 0, 2, 4, 0, negative 3, 1, 2. Changing those two columns, exchanging two columns. Now, I'm not used to doing that. It just feels awkward and weird and strange. But it's okay to do with determinants. And now you see this is upper triangular. What's the determinant of that? 8. The negative, because you exchanged two. So that's also negative 8. Okay, which is easier? I don't know. They're both so easy. Either one of them is fine. Okay? It may actually have been a little more work to do the other one. Okay? Don't know. All right. Now, I'm going to go on and delete this. Is that okay? All right. Here's another one. We'll define the determinant of this. I swear this is so aggravating. My cord gets caught on my ID badge. 2, 3, negative 5. 4, 1, 0. Negative 2, 4, negative 3. Okay. All right. If that's the one I want to operate on, find its determinant. Nothing super easy here. If I weren't thinking anything else, I would think that row wouldn't be too bad. This column, a little worse, but not too bad. But neither one of those are very enticing. But what you might notice is that this row, you can divide by 2, right? Okay, that column, okay? Well, let's see what that does for us. And, I mean, just the notation makes it look like it makes sense. Take the 2 out here, and that leaves us a 1, 2, minus 1. 3, 1, 4. Negative 5, 0, negative 3. Okay? Now, didn't make taking a determinant a lot easier, but now you can row reduce fairly easily, right? And the row reduction doesn't do. Dividing by 2, divide that one by 2 too. In other words, yeah, that is going to do the same thing. But now when we do your row reduction here, that's not going to change the determinant at all. Okay? So what might you want to do first? Get this to be a 0. How would you make that happen? To get the 2 to become a 0, what would you do? Oh, come on, huh? Row 2 minus 2 row 1. Right, okay. So don't forget your 2. You already pulled it out, so don't forget about it. Write down the first 1, 3, negative 5. And what's your second one? 0. Negative 5, is that right? Okay. And 10. Okay. And what might you do to the third one? And see, you don't change the determinant at all by doing this operation. Nothing. Okay. And what might you do for the bottom row? You want that to be a 0 too, don't you? So what do? Just add them. Row 1 plus row 3. That's all. And what does that give you? 0. 7. Negative 8. Okay? I don't care for this much at all. Do you? Frankly, rather than reducing any further, I'm just going to take a determinant of that. Okay? It's probably not what the book does, but I'm going to do 2 times. Now the determinant here, I'm going to use that column. And of course, that's going to wipe out that row. And that is a 1 in the primary position 1. So I think I'll change this to a parentheses here. 1 times, and then this is 40 minus 70 is 2 times a negative 30, which is negative 60. Boy, that's a huge number, isn't it? You know what? They didn't even do it. Shame on them. They just showed you could do that. Well, we took it the next step and actually showed what we got. Okay? So I should pay closer attention to what they're doing in the book. But yeah, that's exactly how you go about doing that. Want to do example 3? Sure we do. Okay? I can't find my cursor. There it is. Can I erase? Okay. Find the determinant of this one. Here's matrix A is negative 1, 2, 2, 3, negative 6, 4, 5, negative 10, negative 3. Okay. Make sure I did it right. Yeah. Okay. can you see anything that may make taking a determinant easier? Because no zeros in here, you're going to have either expand it and go, which we could do. We've done it before and we can do it again. But is there anything that might make it a little easier? Second?
Since you have -1, you can just reduce everything by multiplying.
Okay. You want to make that -1 a 1? Is that what you're saying?
Right.
Okay. That's certainly a doable thing. Okay? But let me just suggest something else to you. Notice that 2 is, this is -2 times that. This is also -2 times that. And this is also -2 times that. So, why don't we multiply, because you're not used to looking at columns this way, but you know, get used to it, okay? Now, if you were to multiply, do column 2 minus 2, plus 2 times row column 1, what you're going to wind up with then is what? Second? 0, 0, 0. Guess what that means? The determinant 0. Because you go down that column and you don't have anything to do. 0 times 0, 0 times everything. So this is one whose determinant is 0. All you have to do to show that is multiply, like we said, column 2 minus 2, plus 2 times column 1. Is that a 0? Is that a 0? Is that a 0? Right? And once you see a column or a row of zeros, you know the whole determinant. So let's do column 2 plus 2 column 1. Okay? And that would be a -1, 0, 2, a 3, 0, 4, and a 5, 0, -3. I mean, check it and see. I think it's right. 2 plus or minus 2 is 0. 6 minus 6. Whoa. No, 6 plus 6 is 0. And -10 plus 10 is 0. Yeah. And once you have a column or row of zeros, the whole determinant is 0. Okay? And that leads again, and for those of you too that were in the differential equation class, we saw that anytime you had a multiple of one function was a multiple of another function, that led to linearly dependence. That's exactly what you got here. Okay, mixing the two classes. Okay, and we're going to get to it too, by the way. Okay. Now, do any of you like Sudoku? Sudoku? Yeah. I'm almost hooked on that thing. Okay. Guess what? How did they develop that? Matrices. That is a matrix. A 3x3 matrix. Okay. So this little game, number placement puzzle Sudoku, object, blah, blah, blah. For a completed Sudoku grid to be valid, blah, blah, blah. So, direct result of condition 2 of theorem 3.4 on the next page. So we haven't quite gotten there yet. So I guess we ought to get there. Okay, let's do top of page 115. All right. Example 3 showed us When two columns of a matrix are scalar multiples of each other, the determinant has got to be a 0. This is one of 3 conditions that yield to determinants of 0. And here's theorem 3.4. If A, of course, is a square matrix, has to be square or else you can't even talk about a determinant. And any one of the following is true. Then the determinant of A is 0. Okay? If any one of these is true and it's a square matrix, an entire row or column consists of zeros. Okay, if a whole row or whole column is zeros, the determinant is 0. Gotta be, okay? Number 2, 2 rows or columns are equal. Okay, and number 3, 1 row or column is a multiple of another row or column. Okay, those 3 are going to make it a 0 determinant. Okay? Any questions? Let's just show a few of these. What's the determinant of 0, 0, 0, 2, 4, negative 5, and 3, negative 5, 2? What's the determinant? Zero, okay? I'm going to choose the first row. 0 times this is 0, plus 0 times this is 0, plus 0 times that is 0. Yes, you have no choice, it's a 0. Okay. So if a row or a column are zeros, you got it. Okay, how about this one? That determinant is 0. Okay, how about this one? Determinant of 1, negative 2, 4, 0, 1, 2, and 1, negative 2, 4. What's that determinant? Zero. For about 3 or 4 reasons, okay? Number 1 is these 2 rows are identical. And anytime that's the case, your determinant is going to be 0. Another would be these 2 rows are multiples of each other. Right? Double, negative 2 times this is that, negative 2. No, it's not. Is it? Not quite. I'm sorry. That's the reason the two rows are identical. I thought they were another reason there, but it's not. Sorry. Okay? And so that determinant is 0. And then the last one is 1, 2, negative 3, 2, negative 1, negative 6, and negative 2, 0, 6. Okay? What's the determinant of that one? Say again?
0.
Why? Yes, column 1 and 3 are multiples of each other. Negative 3 times that is negative 3, negative 3 times that is negative 6, negative 3 times that is positive 6. Yes, multiples, 2 columns or rows are multiples of each other. The determinant is 0. Okay? Whoa, how did that happen? I thought I had plenty of time to do. We will do example 4 next time, okay? Homework exercises here would include any of the odds 1 through 19. Now, there's a whole bunch of those and some pretty big matrices included. Then do either 21 or 23 or both. And any of the odds 25 through 35. Okay? Might try 37 as well. That looks pretty straightforward. Okay, and we'll stop there and pick up the rest of them next time. All right. Good deal. And by the way, if you haven't noticed, Chapter 3 goes along pretty quickly, okay? And we only have, well, we have a little bit more to go. So I was thinking there were only 3 sections, but there are 4 sections here. Yeah. So we're almost halfway through the chapter, so we'll pick up and go from there. Any questions? Good deal. We will see you Thursday.